Raphael was born in Bern and then spent 10 years of his youth in Hong Kong. He did his master's degree in theoretical physics at the University of Bern in 2012, and his PhD also at the University of Bern in 2017 on multi-instrument Rosetta data analysis and simulating the gas and dust comet of comet 67P under the supervision of Professor Nicholas Thomas. Since August 2017, he has been a postdoc at the International Space Science Institute. And his talk is on Rosetta, the journey to a relic from the early solar system.
So good evening, everyone, and let's talk about comets. Comets have actually been one of the mysterious objects that have been known to man for really millennia. So we have observational evidence of that going back to the ancient Chinese, to the Iron Age, and to the Roman Empire and Roman Republic. And because we couldn't really predict when comets would were observable, they were often seen as bad omens. And it was only really later that we figured out that their tails always pointed away from the sun. And Isaac Newton, with his theory of gravity, could then explain that they were actually on elliptical orbits around the sun. And just a few years later, it was Halley who actually predicted the first comet that would come back, and it's a comet now called after him. So since then, comets, you might have seen them yourself like this. We know them to contain a lot of ice, mostly water and CO2, and dust. And as they come close to the sun, they start evaporating and ejecting dust and producing these wonderful dust tails that you can see with your naked eye. So, what's Rosetta? Well, even though these large tails span millions of kilometers, their origin is just from a very, very small nucleus. So you can see some examples here. And you can see the scale bar here is just a few kilometers, and these small objects produce these large tails. And until recently, it was only possible to observe comets from ground-based observations, and it was only 30 years ago where it was the first time where we flew close by a comet to actually see what these nuclei look like. And the European Space Agency's mission, Rosetta, was the first to actually catch a comet and escort it into the inner solar system to really observe it in close proximity for 2 years. So here you see a picture of the target comet of the Rosetta mission, 67P Churyumov-Gerasimenko. You can see the coma and the long tail of the comet, but we're actually not interested in that. We're really only interested in the very center, what's inside there. That's what we actually want to look at. So having a spacecraft in close proximity really gives us the opportunity to look at the surface and the innermost activity in much detail. You can see here the comet, which has a really strange shape. It kind of looks like a duck, rubber duck. The rotation axis of the comet is inclined to the orbital plane, very similar to the Earth's. And so that results in seasons, as we know them, not as we know them on Earth, but seasons not unlike on Earth. It's a very small object, as I mentioned, only 4 kilometers across, and its density is really small. It's only half of that of water, so if you would plunge it into an ocean, it would actually float. And we can take these wonderful pictures of the surface of the comet. So the Rosetta spacecraft is actually a suite of instruments that you can see here with large solar panels, but you can actually maybe a better analogy is something like this. So we're actually, each instrument is kind of like a blind person trying to examine this comet and see something a bit different. And it's our job as scientists to kind of bring that together and understand how this actually makes sense, and so that we can understand how comets work. So why should we even consider, studying comets? Well, the important thing to understand is that during the early phase of the formation of the solar system, the protoplanetary disk, which you can see a simulation of here, which contains gas and dust, the small dust particles would start to agglomerate and start to grow into small grains, and then larger grains, and eventually into kilometer-sized objects called planetesimals. You can see such formation in this simulation here. At some point there will be some small clumps coming up. And essentially these planetesimals would then go on to become planets, but of course not all of them would actually end up being in planets, and the remnants or relics of this process are comets and asteroids that are preserved until today. So studying these objects gives us the opportunity to look at the objects from the formation of the solar system. So they help explain one puzzle piece of how we got here. And one of the questions you might want to answer is, did maybe comets bring life onto Earth? And of course, we wouldn't really expect amino acid, and is actually a part that builds DNA, for example. So this is quite an exciting discovery that we made with Rosetta. Now, comets are not only interested for questions of how did we get here, they're kind of interesting for themselves because they are very dynamic and very active. And as I've told you, as ice sublimates, it drags dust particles from the surface, and you can see a simulation how these particles actually get sprayed out into space. And as they spray out into space, you can actually not directly see them, so this is an image here, but because the light is reflected on these particles, if you enhance this image, you can then appreciate the inner dust coma of the comet. So this is all dust coming from the surface and escaping into space. And because we monitored the comet for such a long time, we were able to really see a firework of dust ejected from this comet. And it's something interesting about it because as the comet rotates, different dust is emitted, and actually there's some dust features that reoccur daily, and you can pretty much predict them very precisely. But then once in a while, there's a very violent ejection, and it comes here, and those just happen sporadically, and we don't really know why or when they happen, but they're very violent and eject a lot of gas and dust. And all this activity results in a very diverse surface. So we didn't really imagine to find a surface that shows so many different types of surfaces. So we have large cliffs, as you can see here, that almost resemble cliffs that we see in the Alps. So it almost looks like an Eiger Nordwand type of thing on the comet. The size is actually almost comparable. And then very dusty deposits, like you can see them here, of smooth material, very small grains, that actually get ejected during the summer on the southern hemisphere and then get reaccumulated on top, and they build up these dusty deposits. There are also weird sinkholes and pits and terraces, so there's really a lot going on this comet that we didn't really expect. And there are some very interesting regions on the comet. You can see on this 3D representation, this green area is a very active area. And in particular, you can see here that in this image from 2014, end of 2014, there's this region here that is very well covered with dust. And then just a year later, all of this dust has been removed. And you can see this kind of small point there is actually a boulder that has been totally excavated. In the same region, you have almost cyclical changes. So you see this structure here, this kind of meandering feature, and as time progresses, we see this small feature arising here, and just within a few weeks, this actually grows hundreds of meters and then vanishes again, pretty much cycling back to the initial state. And then the activity is actually that intense that in some places we're moving boulders pretty much the size of this room. So you can see there's a boulder here, and when we reobserved it, it actually moved 200, 300 meters across over here. And those are really huge boulders. You have to appreciate the size part here. Those are not just pebbles you're moving. And then there are features that are really puzzling and look very strange, like this thing here kind of looks something you might have on your plate in the morning. So we have kind of some pancake structures here. Also, due to the activity, there are large stresses in the comet, especially in this neck region, the blue region here. And due to these stresses, the comet actually starts cracking apart. And you can see this here, this large ridge here, and a year later, or more than a year later, it has really extended, and we've actually gotten a new fault line here. So the comet is actually, its shape is realigning, and thus really destroying the shape as we know it now. And then there's something I think no one expected, because I should say first, the comet has no atmosphere. So you wouldn't expect something like this. If you zoom into that, those are dunes. So, and these are tens of meters long and a few meters high. And in an atmosphereless or almost atmosphereless body, you wouldn't really expect that. So this is still, it's still ongoing research to explain how we still get this in an almost atmosphereless body. So just in case you need some travel advice or would like to do some dune surfing, maybe consider the comet next time you. But why bother? This is all nice. We have nice pictures. This doesn't really affect us, right? Well, not really. So comets can actually be hazards not only for Earth, but also for spacecraft. Because as you can see in this simulation here, the dust that is ejected gets spread out in the inner solar system, and if we were to fly through that and hit the dust, we can damage our spacecraft or destroy them completely. So especially kind of in the backdrop of us potentially becoming an interplanetary species and starting to travel around with humans in the solar system, we would want to know where are the risks of these dust particles that could potentially be fatal for us. Also, due to the activity, the orbits of comets are really, really badly predictable. So we don't really know where they're going, because other than just normal gravitational objects, their activity actually changes their orbits. So we don't really know where they're going, and if we don't know where they're going, they might hit Earth, which would be bad. So understanding how comets actually propagate in time so that we can predict where they are is really important. So we don't want this here to happen. We don't want to destroy our spacecraft. And I think we certainly don't want this to happen. Or I'd say at least if that happens, we would want to predict it, that kind of everyone can update their Facebook statuses or whatever. So with that kind of happy note of us all dying in a giant impact, I would like to thank you for your attention, and I'll be happy to take some questions.